Hello, my fellow YouTubers. This is Roy back again, and my buddy Monkey George. Alrighty. A little more balancing going on between the outside stator and the rotor. Let's go ahead and jump right into a cool experiment. You guys ready? Make sure you leave your comments. Alright, so what are we doing here? We are going to talk about this pole on this magnet is the south. The lens effect is causing the opposing pole to appear in this iron in front of it. By that being done, it's putting the opposite pole of what's appearing here. So if this is south, this would be a north, this would be a south. Now let's go out here and let's see how the compass is reacting being this far away. Remember, there's a metal band that goes around, so let's go ahead and turn it. So that's the north there. It's the south. It's the north. So let's go ahead and put this coil I made, 1/4-inch iron bar. We're going to set it up to where we're not touching, just so we create a, in fact, let me go ahead and put these wires together. Something's telling me to put them together. So we're going to put them together. Okay. So let's go ahead and we're going to create a little gap. And the compass hasn't moved. Now let's see if the compass reacts a little bit better. Okay, well, this is where the excitement comes in. So, let's stop it here. There's a south pole. So there's a north pole there. There's a south pole there. And then, let's unconnect this because I think it's dead short in it. Alright, so we're still not touching. And compass right up on it. Oh yeah. So we're dead short now, connecting the wires. Alright, so here you go. So you got your south up there, your north, your south here, and then you got your north showing up, no, your south over here. Remember, you got your south, we're starting with a south. We're flopping and a dipole, so this is going to be north and then south. And now we're going in inductively into this coil. And that means that would be south, north, and this would be the south again. There's your south. Is that amazing? And let's turn and see what happens. Let's get some juice in there. Just let it turn a little bit. There you go. to get back to the north. All right. Seems like you almost have to be, the north has to be running. You see that, right? So there's your north, there's your south, there's your north, there's your south, there's your north showing up again. Let's see if we can get a little charge. So we're extending on out inductively. This is all important stuff, guys. The reason I'm even posting these videos, I want you to see the process. This is an experimental phase here. I call it the College of St. Vincent. And this will show a lot when it comes to the dipole, which is very important, especially with vacuum. When I start digging into the vacuum again, because I got some, what do I got over here? I got my vacuum pump, and I can make a chamber. And what we can do is we'll start off with this simple stuff. Experiments on why does water in a chamber when it gets under vacuum, it disappears. It steams away. So you guys leave your comments on that before we do the test. I want to hear what you have to say. Why does water, as soon as we get it under vacuum, it steams up and disappears? Something very important there. Thermodynamics is all part of this too, guys. It's a combination and understanding on the ground itself, on how to suck on its nipple and get the damn juice out of the nipple, because you just have to know how to suck on it, and nobody's been sucking good. So we're here to suck out of the ground. This is all about the ground, but we're right now learning how magnetic fields react and how they're designed, and really how you create this field. It's almost like artwork, because my head is in the game with the field itself, the magnetic field. I'm gonna get me some magnetic paper so we can kind of see visually the streams. But if you see how you branch out, you can see how this becomes a cog in a wheel, and this becomes another part, and then another part, and you also see it branching out, and it all works together. So this is how the circuitry follows nature, which is going to work towards the grounding pipes. Because remember, we got the ground pipes that I pulled out that are sitting here just waiting for me, and to put the system in the ground. Remember, we got the buzz box. We're taking low voltage, making super high voltage. We're going to separate it, like Ed says, and we're going to make electrostatics. We're going to couple. That's why we're talking about this as well with electromagnetic coupling. We're talking about electrostatic coupling, and that's how we're going to be sucking on the nipple of Mother Earth. It's electrostatic coupling. That's what she's used to. It's all she wants. The stimulation of all stimulations is electrostatic. And that's why electrostatic is important. If you want to know how to suck on that nipple and pull that juice out. Let's move on. I'm getting excited over here. Stop sucking on Earth's nipple. You can see how we're creating dipoles. So from a magnet, no battery, no nothing going, magnet, how it's reacted to the iron, how the iron now has I formed another dipole, and I flopped over well, obviously, to create a new dipole, it's always going to be the opposing field. So you're always branching out from the opposing field. You can see what created it and where the end game here is. So if this is a north, this out here should be north, which is faced a little sideways, but there you go. It's pulling towards north. So it segregated itself here. It created this is what's amazing to me. This magnet to this iron created a magnetic field that's opposing. That means it basically is creating a mirror image for itself. It's sort of creating life for itself. It's what's ahead of it when it's a magnetic field. Something about that. Leave your comments. All right, you guys. So the other thing here is got doubled up all the way around on the cores except for 1, 2, 3, 4 sections. And I got 20 linear feet of 3/8 thick by 4 inches tall steel bars. About 20 feet. So I'm a couple short. So we'll get those when I get to them. Wanted to show now, like now we doubled up. So now you got some more iron, which is more surface area from one to the other, which is really cool. So the way these coils are set up on here is this is where I started. This is a south pole. So that means this would be wound counterclockwise. So you can see I started. It goes down the bottom, winds that way. So when you put a positive on this side and a negative on that side, this coil would be a positive or a plus. This would be the negative. This one's wound clockwise. So when it comes up from the bottom, it turns clockwise. So when you turn the wire clockwise, it creates its pole. One more experiment that I just thought of is let's see if this wire that's on here can change the pole to be what it isn't. So right now, let's see, how do we prove that? Because if we're always flopping poles here, all right, so that's north, it says, right? And there's your north, and it's north. So if we remove this, you can see we lose a little bit, and we just turned it over. It's still north. So it seems like in the electromagnetic version, without putting juice through the wire, say the back door entrance, this would be, is it doesn't change its what it is until it goes through the wire. You understand what I'm saying? Like we just flipped this. It's still north. It's still north. So basically the wire did not, but if we connect the two wires together, let's see what that does. These little experiments are very important because you stumble onto something and then you get an aha moment because maybe when these wires are connected, the field's bigger. And let's see what we have now. So do we have north still? Yes. And let's flop it and still have north, right? Yes. Let's see if we flip it a little bit. Here's the south. And the south gets strong as you try to tear away from the iron because you're stretching like a spring, which is really neat. So you can see how it reacts. So we're pulling to the south as we stretch away, and all of a sudden you stretch, it snaps back, and now we're at a north. Well, I'm confused. That's a south-north, so that's a south. That's what it says. And you can see how cool stuff. So now having metal all the way around it pretty thick except for those 4 areas, if you put the positive through one side, let's put a little 12-volt battery in here and see what I can get away with for a second here. So I got one hand, right? One hand. So it's got a lot of pull strength. So let's see if I can. See, I'm just hand tapping it so I don't. Now, think about this. This is just the reaction between the magnet. So if I can control, I can do whatever I want with this thing. Forward, backward, forward, backward. So a controller on it is one of the experiments. Also now, juicing up the inside so it makes motion. What are we going to have here? So think about this. So we're talking about stretching out dipole. We're looking at where the poles at what positions end up. We know they're rotating, so that means not only are we having a push-pull kind of thing going, we also having a rotation this way. And that rotation with the wheel turning, which I'm going to disconnect this. Let's get this to the side. With that wheel turning, and with this dipole here, let's talk about the wave for a second. So what's happening here is you're having a dipole there shooting in and out this way. So it's shooting out streams. When it shoots out streams, these streams now, when they get to the second location here, they're flipping their poles. So they're bouncing back, but these on this side is now projecting outward. Now it goes to the next section, which would be here, and it does the same thing. Sort of reminds me of telepathic, or not telepathic, but yeah, how radio waves work. Well, what you also have here is a sine wave that is going from this side to this side, to where this iron is the dipole like this. So this 4 inches that we have here becomes the dipole. So underneath this bar, there's a negative wave that's traveling and going down, like going down to the ground, and it's also coming back up and coming up on the other side. So that magnetic field as a inductive force, like this is small, but this gets bigger because as you put juice in here, you create that electromagnetic force that's going to go from underneath the wheel inductively to the ground. On top of that, you have the same thing that's going to be coming upward. It's going to come up and come around. The stronger the field, the higher the peaks, and lower the valley. But the valley is what's important, because if we were looking to levitate stone, just say, or anything, but just start up with stone, something that's non-conductive, and obviously through experiments we know it's magnetically collective, meaning that it can be inductively magnetically charged or discharged. It can't be altered without a high frequency radio wave, but it can be changed internally with its molecules to where one side could shoot over and cause another dipole, and that dipole would be the levitation of the rock, say forth. So if you have Ed's tripod and you're coming down the tripod, like Ed has here, the tripod, and you're coming down with the cables, and then he has a metal rod that shoots through Ed has a metal rod shooting through the boulder. So he drills a hole through it, he puts the metal rod, and he puts the two cables on it. So if that signal that he's sending out is going to the rock, and the rock with the iron core going through it would unbalance as an inductive alteration of the molecules in the rock should flip its poles on the ground. And what would have to happen is this: the ground cannot be neutral as it is. It would have to be subjective to electrostatic field, which would put the opposing field to the surface. For instance, the surface of the ground is predominantly negative. That's because under normal conditions, the air is positively charged. So under different conditions, such as clouds, that would cause the ground to react inductively, electrostatically, would cause the ground to put up the opposing field of whatever the bottom of the cloud is. So if the bottom of the cloud is going to be a negative, then what's going to happen is the negative in the ground is going to shoot down, lower itself underneath the canopy, we'll call it, and the positive is going to stay more to the surface. So we're taking the ground and treating it just like we are when we take electrostatic induction, and we take three boulders, and one's neutrally charged, one's positively charged, one's negatively charged, and then we take the boulder that's neutral and we can alter its molecules by not even touching inductively. That's the way this is going to work, guys. Leave your comments. Peace out.